Hello everyone. In this video we will continue to examine topic 5.1 electric fields. So we covered this a little bit in the simulation in the last video, but I wanted to sort of apply our concept of the electric field to our equation and our physical representation of the electric field. So imagine you were using the electric field line representation to first show the electric field due to a negative point charge, and then two, determine how it would act on a small positive charge brought near it. Okay, well, that negative charge using the electric field line representation just has arrows pointed inward that get closer and closer together as the field gets stronger. But what happens to a small positive charge brought near it? Well, we've already studied that. We already know sort of fundamentally what happens. That small positive charge will feel a force towards that negative charge, okay? That point negative charge. And that force you could calculate using Coulomb's law. But you could also calculate it if you simply knew the electric field, okay? So if you know the electric field, that purple representation, you can calculate the force on that small charge by remembering that what the electric field does is sort of, it's produced by a particular charge, and then that electric field sort of reaches out and applies the force to the external charge. So we rearrange the electric field force definition, which was initially E equals F divided by Q. Very simple algebra. That gives us Fe equals Q times E, but this is a very different interpretation. Same formula, different interpretation. Now, the electric field produced by that negative charge right in there is interacting with the external charge, that light blue positive charge right here. They multiply together, and that gives you the electric force that acts on the positive charge. So it's a two-step process. The negative charge in the center produces an electric field. E equals KQ over R squared R hat. That's the purple field. Okay? Then that field interacts with another charge, small q, to produce the electric force. And so, although it's a simple rearrangement of the definition of the electric field, this formula in some way is the whole point, because this formula corresponds to our explanation that the way that an electric force is applied to a charge is that the electric field in that area grabs on to the charge and applies the electric force itself, and that happens locally. The electric field at a point only depends on the sources of the field that are not at that point. So these purple lines depend on this charge, and the electric field right there depends on the source charge, but not the external charge placed at that point. So if you know the electric field at a point, you can calculate the electric force on a charge placed at that point using Fe equals Q times E. In many ways, this will be the most useful formula having to do with electric field. Why? And here's the key. If somehow you can figure out the electric field due to a very complicated distribution of charges, then you can get the force on a charge placed at that point without using Coulomb's law. You just multiply by the magnitude of the charge that you're putting there. That's the key. That's the essence of the electric field. I'm going to say that again. If somehow you can figure out what the electric field is due to a different, some complicated arrangement of charges, then to find the force on another charge that you put in that vicinity, it's very easy. You just take that electric field and multiply by the magnitude of the charge that you're putting there. That's key. One more thing to remember is that the electric field is defined as the electric force per unit charge. So of course, when you multiply by an amount of charge, you get a force. Okay, so big question then. How do we calculate the electric field due to multiple charges? Now, There's going to be a straightforward answer to this, although in practice this can get algebraically kind of annoying. But the general idea is that we're using that principle of superposition again. This is an idea we first saw in gravitational fields but really hammered home in waves, and that's the idea that to get the electric field at any particular point, okay, any point at all, you add up the electric fields that are due to the individual sources. So what does it mean? If you have multiple sources of field, okay, so for example, what is called a double charge or double positive charge, two positive charges producing field, then the field at any particular point will be the field due to one of them, which we have a formula for, plus the field due to the other, and that sum is the superposition of the fields. That gives you the net electric field. Okay, so you calculate the electric field at any point by adding up the electric field due to each of the charges contributing to the net field at that point. Okay, that's the general idea. That's the idea of the principle of superposition applied to this case. So let's say, for example, we want the electric field for a double positive charge, okay, at different points. How do we do it? Well, let's consider this point right here. To find the electric field right here at this point, first we're going to say, oh, we have some electric field from this charge, E1. It's small arrow and pointing away from E1. We also have some field due to this charge, E2. It's a larger arrow pointed away from charge 2. Then we add them vectorially, okay, because this is the sum of these electric field vectors. We take E1, add it tip to tail to E2, and that gives us E net, the net electric field at this point. So the net electric field right there is actually slightly up. That makes sense, because if you put a little positive charge right here, it's going to feel sort of pushed upwards, but a little more away from this one than from this one. That's why you have that sort of bend. And each magnitude of those arrows, okay, E1 and E2, are both calculated separately using our electric field at a point formula, which is KQ over R squared R hat. So we can calculate the electric field due to each one of these charges separately, and then add them like vectors. Okay, and the end result is a field pattern that looks kind of like this. And that's actually one of the ones you want to be able to draw sort of offhand. So if I have a double charge, okay, you want to be able to draw it, not necessarily from memory, but sort of thinking about every particular point and perhaps drawing an electric field of arrows. Okay, and you can get a sense of that here. All right. So I'll come back here. All right. By considering lots of different points and how they interact. And to draw that with electric field lines, we have these curved lines coming out, up, and away. Okay, and it never has to be perfect. One thing to note is that the electric field at any particular point is not curved. Okay, it can't be curved. There's no such thing as a curved vector. But these curved field lines indicate that the electric field right here is tangent to that curve. So that's how the electric field lines work. So if it's curved away like this, then the electric field right at that point would be tangent to the curve, just touching that curve. And you could, in theory, find the electric field at any particular point using this technique, although that would take quite a while. That is one of the virtues of simulations. Other two really important electric field distributions to know and be familiar with is the electric dipole, that's a single positive and a single negative charge, and the parallel plate capacitor. We're going to come back to this big time later, but that's when you get a whole bunch of positive charges lined up against a whole bunch of negative charges. Okay? And in the next video, I'll spend a little more time talking about the structure of these three charge distributions and what they look like.